तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. Last time I had introduced the phasor version of the Poynting theorem, and then I had started with looking at what happens to waves when they enter a lossy dielectric. Now we have looked at the wave in vacuum, and we have looked at the wave in a good conductor, and this is the third case, which is a wave in a bad conductor. So we still have our wave equation, and the wave equation is still curl of E, which is minus del squared E, but applying Maxwell's equation to curl of E, it becomes curl of del B del T, which is minus sign minus mu times curl of H. Now because it is a material and not a vacuum, curl of H gives me two terms, the current density plus del D del T. Now in skin effect, good conductor, I neglected this term. In vacuum, I neglected this term. Now what we are going to do is we are going to keep both terms, and we are going to assume that this term is small compared to the other terms in the expression. So my wave equation becomes del squared E is equal to, and there is a del del T, sorry, mu del J del T plus mu epsilon del squared E del T squared. Either converting from E to J or from J to E, we get a wave equation. Let us convert from J to E this time. Last time I did it from E to J. So that gives me, using J equals sigma E and substituting in here, I get del squared E is equal to mu sigma del E del T plus mu epsilon del squared E del T squared. So this is the wave equation. It includes vacuum where this term is missing, it includes skin effect where this term is missing, and now we are going to do the full equation where both terms are present. But as I said, I am going to assume sigma is small. So this term is less important than these two terms. Now I am going to look for simple waves. So I am going to assume that the electric field E is some E naught along the x direction e to the j omega t minus k z. So the wave is going along z with a frequency omega, a wavelength 2 pi over k. It has an amplitude E naught along the x direction. So therefore h is going to be some h naught y direction e to the j omega t minus k z. If I substitute this into the wave equation, what do I get? Del squared will become minus k squared, because del del z will pull out a minus j k, and minus j k squared is minus k squared. del t will go to j omega, because when I differentiate with respect to t, I will pull out a j omega. So, substituting all that into my wave equation, I get minus k squared along the Ex direction is equal to mu sigma j omega Ex minus mu epsilon omega squared Ex, because if you look back at this equation, del squared became minus k squared, del t became j omega, and del squared del t squared became minus omega squared. So, if you look at this equation, well, you can always solve it, E goes out. So, you get a general expression which is k squared is equal to mu epsilon omega squared minus j omega mu sigma. And you can analyze this equation and solve it as you like. But there is a more useful way of looking at this equation, and that is to pretend that this piece is a part of this piece itself. So, that instead of having two terms, I just modify one term in this equation and include this effect. For that, what I am going to do is I am going to combine these two expressions. I know for my material, which is a lossy dielectric, this term is more important. That is to say, it is a high frequency, low conductivity case. So, in that case, what do I get? I will get is equal to minus mu epsilon omega squared times Ex. Now, this term is just 1, because all the terms corresponding to it are already outside. So, it is 1 plus, well, for this term we will put in the numerator mu sigma j omega, but we will have to divide by this term, which is extra. So, divided by minus mu epsilon omega squared. So, the first term will be Ex times minus mu epsilon omega squared, that is this term. The second term, the denominator and numerator cancel. So, it will be Ex times mu sigma j omega, which is this term. So, I can cancel out a few terms there. So, that becomes minus mu epsilon omega squared times 1 minus mu cancels, 1 factor of omega will cancel. So, that leaves me with j sigma divided by epsilon omega times Ex. Now, I have done nothing here except collect terms, but I do know that this term is small, because I have a small sigma and a large omega. And what I am going to do is I am going to absorb it in one of these material constants. By convention, it is absorbed into epsilon. So, I am going to write this equation as minus k squared Ex is equal to, let me rewrite this, minus omega squared mu epsilon times 1 minus j sigma by omega epsilon times Ex is equal to minus omega squared mu epsilon effective times Ex, where what is epsilon effective? Epsilon effective is the real epsilon times 1 minus j sigma over omega epsilon. It is just a convenience. There is nothing in this equation that is not there in this equation, there is nothing in this equation that is not there in this equation. What we gain, however, is that this equation we know fully. We have already looked at it, we know all about it. Since we know all about it, we know the answers can be written down simply. We know that this will give me an answer which says that k is equal to plus minus omega square root mu epsilon effective. So, if I know my frequency, I can calculate k, and in that case I know my electric field, because electric field E is E x along x, which is E naught along x direction e to the j omega t minus, but I have a plus minus here, so I will put minus plus omega root mu epsilon effective z. So, for given omega, I know how the wave depends on z, and this is nothing but my expression for k. Now, we have not actually achieved anything. I mean, we have hidden all the complications in epsilon effective. So, what have we gained? Well, we only gain if this term is very small. Let us suppose that this term is very small. Then I can simplify this expression. That is, I can say that k, which is equal to plus minus omega root mu epsilon effective, is actually equal to plus minus omega root mu epsilon, epsilon effective I am writing out, times square root of 1 minus j sigma over omega epsilon. If this is very small, I can do a binomial expansion. Square root of 1 minus x is equal to approximately 1 minus x over 2. That is, it is 1 minus x times the power of the radical. In this case, square root is power half. So, half comes out. There are other terms to this binomial expansion, but we are assuming x is so small, only the first term is important. So, I can write this as approximately equal to plus minus omega root mu epsilon times 1 minus j sigma over twice omega epsilon. That same factor of 2 has come out. What have we gained? Well, what we have gained is the following. I will write it on this board itself so that you can see. So, the electric field is along x, it is some E naught e to the j omega t minus plus omega square root mu epsilon. Now, we write this piece out, times 1 minus j sigma over omega epsilon, the factor of 2 in the denominator, times z. Now, I am going to take these two terms apart and let us write it out separately. So, it is equal to E naught e to the j omega t minus plus omega root mu epsilon z, and then I have this term which is minus j squared is minus 1. So, minus j squared is plus 1. So, I just have the minus plus coming out, omega root mu epsilon times j sigma over omega epsilon twice omega epsilon z. All of this is in the exponent of the exponential. Sorry, there is no j there, j has been removed. I had j here, a j there. So, j squared was minus 1, this minus absorbed that. So, this is pure real, whereas these are imaginary terms. So, what I have is a wave whose amplitude is E naught, there is a phase term which represents the wave, and now I have a real exponent coming out into the equation. So, let me combine the real exponent with E naught. So, I get it is E naught e to the minus plus omega root mu epsilon. Now, this omega will cancel actually, but I will write that out first, sigma over twice omega epsilon z times e to the j omega t minus plus omega root mu epsilon z. This is the wave as we normally know it, omega t minus plus k z, but there is a new term here, and this new term has come because of this sigma over 2 omega epsilon term. Now, you can simplify this term by cancelling out omega and by bringing the epsilon into the square root. I am going to do that in place. So, I am going to cancel the omega, and the square root of epsilon over epsilon is 1 over square root of epsilon. So, this piece is going to become square root of mu over epsilon times sigma over 2 z. So, the omega cancelled, the mu came out, square root of epsilon over epsilon became a square root of epsilon in the denominator, and the factor of 2 is down here. So, this exponent does not depend on omega, it does depend on sigma, and it depends on the material properties of the medium. And you see that there is a minus plus to it. So, if I drew this wave, what does it look like? Now, if I had a wave with uniform amplitude that did not change, I can imagine drawing it like this, the uniform amplitude, this is z. So, the amplitude remains constant in z. If I took the minus sign here, then I would have an amplitude that did this, that is, the amplitude is decaying with z, again this is z. If I took the plus sign in this exponent, then I am going to start small, it will grow. So, this is now a case where the amplitude grows. That is because e to the power of plus x grows with x, e to the power of minus x decays with x. So, I have a wave whose envelope, whose amplitude is either increasing with z or it is decreasing with z. But this is a bit confusing, because the energy in the wave is whatever we put into it. How can the amplitude increase? I can understand it decreasing, it gives up energy to the medium because of E dot j due to the sigma. Therefore, energy went away, therefore, the wave decreased in amplitude. But how can the wave increase in amplitude? Yet both solutions are there. There is a decreasing solution, there is an increasing solution. Well, the answer is not complicated. It just has to do with which sign is associated with which sign here. Okay. Now, if you go back and look, they were all together here. So, I could have chosen one of the two signs at the beginning. So, let us say I chose minus. In that case, I would have got e to the j omega t minus omega square root of mu epsilon z, and I would have also got minus omega square root of mu epsilon sigma over 2 omega epsilon. So, it means that this minus sign goes with this minus sign, and this plus sign goes with this plus sign. So, I actually have two separate solutions here, and the solution that corresponds to the minus sign is E naught e to the minus something z e to the j omega t minus omega root mu epsilon z, and the plus solution is E naught e to the plus something z e to the j omega t plus omega square root of mu epsilon z. So, the plus and the minuses go with each other. Why does this help? If you look at this expression, we have seen this before. This is a wave of the type z minus c t, and if you look at this expression, this is a wave of the type z plus c t. So, for the z minus c t term, I get an e to the minus alpha z, where this bracket I am calling alpha. For the z plus c t term, z t wave, I get an e to the plus alpha z. Now, it makes more sense, because the z minus c t wave travels in the plus z direction, and as it travels, it decays. The z plus c t wave travels in the negative direction, and as it travels, it also decays, but it is traveling in the minus z direction, and therefore, it must decay in the minus z direction and not in the plus z direction. So, this growth is a fake growth, it is just out of the mathematics. As far as the physics of the wave is concerned, whichever wave the wave is traveling, in that direction the wave is decaying. It is decaying going into the dielectric in the positive z direction, and if it happens to go in the negative z direction, it is decaying in that direction also. All right. Now, this analysis that we did is an approximation. The approximation we made was here. If we had not made this approximation, we would have had this general expression. For example, if sigma over omega epsilon was of order 1, then we could not have approximated it like this. If sigma over omega epsilon is much greater than 1, we throw away the 1 and we will get back the skin effect. And if sigma over omega epsilon is much less than 1, what we have just done is what is required. But if they are comparable to each other, then you have to be honest, you have to do the full problem. And how does the full problem differ from these two problems? Actually, what is happening is, you have a term which is along the real axis, which is omega squared mu epsilon, and you have a term along the imaginary axis which is j omega mu sigma. So, we have to take these two terms and their combination is the full term, which is what we call omega squared mu epsilon effective. Now, I think I have got my sign wrong, because there will be a minus sign to it. So, let me draw it again. You will have the arrow downwards, so it will be minus j omega mu sigma, and you will have omega squared mu epsilon effective. Now, when you take the square root of this, you get an answer that bisects in angle and is the square root of the magnitude. That is, if you take any complex number and you take its square root, you know that you can always write the complex number as square root of x squared plus y squared e to the j theta, where theta is got from tan theta is equal to y over x. So, then z to the power of half is nothing but square root of x squared plus y squared to the power of half e to the j theta over 2. So, that is why I said the square root of this complex number is bisects this angle. So, theta becomes theta over 2. When this angle is very small, then the overall magnitude is essentially dominated by the real part, in which case when you take the square root, it is like taking the square root of the real part itself. So, that is where we get this kind of solution, where the real part is not affected at all by the presence of a conductivity. The real part only sees the wave part of the equation. But if, for example, in skin depth where you have very little omega squared mu epsilon, then you can't really take square root of omega squared mu epsilon as the dominant part of your real part. In fact, it will be the other part, the j omega mu sigma, that will dominate even the real part of the solution. So, this is an approximation. When you do the real problem exactly, you will find that there is also a slight change in the real frequency. The main change is in the attenuation, that is this term, this is the attenuation, but if you do the problem exactly, even this term changes a little bit. Now, when you write that expression for epsilon down, epsilon is equal to an epsilon real, which is nothing but the epsilon as we know it, and there is a piece which corresponds to epsilon imaginary, which as you can see is in the minus j direction, and it is equal to epsilon real times sigma over omega and omega epsilon, and it is in the negative direction. So, you can put a minus sign there. So, you can see that epsilon is a complex number, and you can talk about a theta, the angle that this complex epsilon makes with the real epsilon corresponding to the medium. This angle is called the loss tangent or loss angle. And it is an important number to know, because when you look at material handbooks, they will not really tell you in the form that you will find these things in equations. They will tell you the loss angle of the material. Effectively, from the loss angle of the material, you are getting the imaginary correction to epsilon real. So, directly you will be able to write down this piece. Okay. Now, I want to go on to a new topic now, and that topic is what happens at an interface. We now know that the wave can travel in vacuum, it can travel in a low loss dielectric, and a low loss dielectric includes a no loss dielectric as well. If sigma were 0, the same equation would apply, and it can travel in a good conductor, that is the skin effect. What I would like to know now is, supposing the wave is traveling in a medium, let us say the medium has mu 1 epsilon 1, and epsilon 1 could be complex taking into account a low loss component to the material, and it meets suddenly a second medium whose properties are mu 2 and epsilon 2. So, both epsilon 1 and epsilon 2 can include any small amount of loss by defining an epsilon effective. Question is, what happens to this wave? Again, let me remind you, we saw two limiting cases. One where this was a perfect conductor, the wave bounced. One where this conductor only differed in sigma, and that too slightly, then we found the wave just went through. Now we want to do the full general problem. Why do we want to do it? This is a very important application. Imagine that this is a light wave, and imagine that this is a piece of glass. So, this could be air and this could be glass. Then the properties of these materials, air and glass, would determine the amount of reflection that you get. So, for example, it is only by understanding this problem that people can make sunscreens on your car, which reflect most of the light and allow only a little light to go in. Therefore, you get very little light on the inner side of the car. Or you could have other kinds of effects. For example, you could have anti-glare coatings on your glasses. They again have to do with how you can play off the properties of two materials and prevent glare from entering the second material. Now, we won't do all of this. We are only going to do a very limited introduction to this problem, but I want you to understand what goes into such designs. So, you have some light entering, some electromagnetic wave entering, some of it is going to reflect, some of it is going to transmit, and perhaps from some further obstacle some of it is going to come right back. So, you have 4 waves that are present at any interface. You have the incoming one, the reflected one, the incoming 2 and the reflected 2. These are the 4 waves that are present. And of course, you do not know exactly what is happening at this interface. Maybe the interface has a few cracks, maybe it has some non-ideal properties. So, this interface is not known. We idealize it as a perfect lossless region. Now, what I am going to do is I am going to enclose this entire region in an imaginary cylinder, and I am assuming this is a one dimensional problem, that the waves are travelling only in this direction, which is z. I am also going to imagine that all the waves have electric field along x, which is say this direction. Coming out of the board is y. So, all the 4 waves have electric field along x and magnetic field along y. You can see that by saying this, we are aware that there are other possibilities. I could as well have electric field along y and magnetic field along minus x. So, it is a these are all the more details you can add to such a problem. Now, let us write down what Poynting theorem tells us about this problem. Poynting theorem tells us that if I take the closed integral of E cross H dot ds, it is equal to the negative of the volume integral of E dot del d del t plus H dot del b del t plus J dot E dV. And we looked at it last time in phasors, and what we found was that if you looked at the real part of this, these two did not contribute. That is, if we have waves that are sinusoidal waves, then we can write down a phasor equation. And what we found was that these two pieces gave only the imaginary part. So, they are reactive, and this piece was resistive or loss. If I assume that whatever is happening at this interface is not really lossy, that is, there is no J, and I average this over one period, then what I am going to get is that this whole thing is going to be equal to 0. In the absence of loss, whatever energy I put in here must come out there or come out here. So, let me write that statement down. My E cross H dot ds, ds points this way here and ds points this way here, and ds points this way at the side walls. You can see that E cross H dot ds does not contribute on the side walls. On this wall, what I get is minus E cross H due to the incident one wave plus E cross H due to the reflected one wave multiplied by the area of this cylinder must be equal to, or well, let me add it up, plus the E cross H reflected 2 wave minus the E cross H incident 2 wave again into area must be equal to 0. There is nothing happening in the bulk of that cylinder, so that is 0. So, it must be the net of whatever is entering must be 0. So, I see two positive terms and two negative terms. So, I am going to take the negative terms to the other side. I am going to let area cancel out. So, what do I get? I get E cross H reflected on surface 1 plus E cross H reflected on surface 2. So, that is these two terms is equal to E cross H incident 1 plus E cross H incident 2. Whatever power is leaving the cylinder, add it up, it is equal to the total power that is entering the cylinder. It is a obvious statement, I am not saying anything profound. You could almost have said it without knowing any electromagnetic theory. So, if you shine a torchlight at an interface with 1 watt of power going in, maybe 40% will reflect back at you, 60% will go through. If two torchlights were both shining, each with let us say 1 watt, and each was reflecting 40% and transmitting 60%, then I would get 40% reflection from torch 1, 60% transmission from torch 2. So, I will get 1 watt back on either side. That is what this is saying. It is saying that reflected power is equal to total incident power. However, this particular way of looking at it is very powerful, and in fact, this is how all advanced treatment of microwave systems is handled, and the approach is called the scattering matrix. You could imagine that I did not have a torch in region 2, I had only a torch from region 1, and I sent in unit amount of energy. Then I will get some energy back from these two regions. So, I could say E cross H reflected in region 1 due to E cross H incident in region 1, the same E cross H reflected in region 1 due to E cross H incident in region 2. Similarly, I could talk about E cross H reflected from region 2 due to E cross H incident in region 1, and E cross H reflected from region 2 due to E cross H incident in region 2. So, these are 4 numbers I can come up with. They represent actually 2 experiments. First, I shine a torch from the left hand side and I measure how much reflects, how much transmits. Actually, I do more than that. I do not measure just power, I measure the phase relationship. So, these are actually complex numbers. If we look at numbers like this forms something called a scattering matrix. Now, scattering matrix is not exactly these 4 numbers, but they are very close to something like this. A measure of how much is reflected due to what is incident on side 1, the same due to side 2, how much is reflected in 2 due to incident in 1, and how much is reflected in 2 due to incident in 2. And this way of looking at the problem tells us how different electromagnetic waves are from circuits. If you had a circuit and you had a lumped element, say a resistor, then you know that whatever current came in would leave, and whatever voltage there was here, there would be some drop, and so you would say V is equal to IR. So, the battery is supplying some power, some amount of that power is lost and the power continues. So, the power is going one way, there is a supply of power and is just slowly getting dissipated in all the elements of the circuit. But here the power actually flows in more complicated ways. Some of the power from the battery is actually reflecting, and if you had another resistor in a high frequency network, what will happen is some of the power will reflect, some of it will transmit, some will reflect off the second resistor, come back, some of it will transmit, some will reflect again, some of this energy transmits, and so on and so forth. So, you can see you will have some very complicated things happening here between elements, and this is where such a formulation is used to simplify design, because usually you have to use these elements to make something useful. You can construct very complex things, as I told you, you can construct anti-glare devices, you can make polarizers, you can make all sorts of interesting components out of such dielectric interfaces. So, in order to understand it properly, we have to do something more complicated. However, what we are going to do is something very simple. We are going to take just one perfect dielectric surface, and we are going to assume that we have only one incident wave, no wave coming back at us, and we want to know what amount of the wave reflects, what transmits. This problem is particularly easy to do. So, we have an incident wave which is E naught along the x direction e to the j omega t minus k z. Because of the minus sign, it is moving in the forward direction. Some amount of that energy is reflected. So, I am going to call it E r, also along the x direction, e to the j omega t plus k z. So, because there is a minus sign, it is going in the plus z direction. Because there is a plus sign, it is going in the minus z direction. And then there is a wave here also. This reflected 2 wave, I am going to call it the transmitted wave. So, I will call it E t, also along x, e to the j omega t minus k prime z. K prime, because the wavelength of light in medium 2 may not be the same thing as the wavelength of light in medium 1. So, I have 3 waves, and corresponding to these 3 waves, I have h naught x hat e to the j omega t minus k z, h r, sorry, this is y hat e to the j omega t plus k z, and h t along the y hat e to the j omega t minus k prime z. I have my E field, I have my H field. Now, I know that at this interface, assuming it is a nice ideal interface, E tangential and H tangential are continuous. I know this from what we had discussed earlier, namely that if I draw Stokes lines at this interface, if I draw a Stokes curve and integrate H dot dl or E dot dl, I can show that as I make this very, very thin, the amount of the surface integral goes to 0. So, I have got that the integral on the left hand side is equal to the integral on the right hand side, which is the same thing as saying E tangential and H tangential are continuous. So, now what is E tangential? E tangential at this interface, the interface I am going to put at z equals 0 is going to be this electric field plus this electric field. So, E naught plus E r along the x direction, I am going to drop this common x direction. At z equals 0, both of them are multiplied by e to the j omega t. So, I do not need to keep the z component, they are both into e to the j omega t is equal to the electric field on the right hand side, which is E tangential in the right hand side, E transmitted again into e to the j omega t. Again this z goes to 0, so this term does not come. I can remove the e to the j omega t. So, what I get is E naught plus E r is equal to E t. A very straightforward equation. This is like saying voltage is continuous. It is the generalization of saying that the voltage on 2 sides of a soldered joint are equal. Now, I want to know continuity of H. So, I say H naught plus H r, same arguments, is equal to H t, exactly the same argument as I used for E. So, I have 2 equations. The only problem is I have 2 equations in 6 unknowns, which is not very useful. But of course, that is not really true. Each of these electric and magnetic fields are related. From my Faraday's law or from any other way you put it, you know that the electric field E naught is equal to eta H naught, E r is equal to eta H r, and sorry, E r, and E t is equal to eta prime h t, where eta is equal to square root of mu over epsilon, and eta prime is equal to mu 1 over epsilon 1, mu 2 over epsilon 2. Where does this come from? It comes from the fact that if you say take curl of E is equal to minus del B del t, then I can write this down as I k E x, so E naught is equal to minus j k j omega mu h. I can take this, I can cancel the j's out, I can take the k that side. So, that gives me E naught is equal to, the sign is not important, omega over k mu times h y or h naught. Omega over k is the velocity. So, omega over k is equal to 1 over square root of mu epsilon. So, it is equal to mu over square root of mu epsilon h naught, which is equal to square root of mu over epsilon h naught. So, that is where these factors come in, and these factors are called impedance. Of the medium. That is because if you look at it, you know that, well, I will come back to why it is called impedance of the medium a little later, because it is a fairly important issue. So, I have 3 connections between electric field and magnetic field, and I have 2 equations connecting these 6 quantities. So, I have 5 equations in 6 unknowns, which is much better, because one equation I know just from saying the input energy is 1 watt. So, I can have one free parameter anyway. My torch can shine brightly or it can shine dimly, that is under my control. So, one of these quantities E naught say can be put to any value. So, I have 6 equations in 6 unknowns. Let me write out those equations. E naught plus E r is equal to h t, sorry, E t, h naught plus h r is equal to h t. Now, there is one problem with this equation. If you look at what we have done, when you write down the connection between E naught and E r, E naught is this way, h naught is this way. So, when I say E naught is equal to eta h naught, I mean E naught along x is h naught along y multiplied by eta. But when I connect E r and h r, my h is in the opposite direction, because E cross h must be the other way. So, I need a minus sign for any reflected wave. Any wave going in the opposite direction must have a minus sign. So, now let me substitute for the h's through these equations and get a second equation in E's alone. So, what I get from this equation is E naught over eta minus E r over eta is equal to E t over eta prime. So, I can clear this denominator, or I can write E naught minus E r is equal to eta over eta prime E t. So, I am going to write those 2 equations out. And let us take a look at it. My first equation is E naught plus E r is equal to E t, continuity of electric field. and then I have E naught minus E r is equal to eta over eta prime E t, continuity of the magnetic field. Now, if I add these two equations, E r will cancel out. So, I will get a relation between E naught and E transmitted. So, I get twice E naught, I am just adding these two, plus 0 is equal to 1 plus eta over eta prime E t, or E t is equal to 2 over 1 plus eta over eta prime E naught. Now, what about E r? Well, let me subtract these two equations, then E naught cancels out and I can get E r in terms of E t. So, I will get twice E r is equal to 1 minus eta over eta prime E t. That is, I have subtracted this equation from this equation. So, E naught cancelled, E r added, so it became twice E r, and subtracting this equation from this equation gave me 1 minus eta over eta prime E t. But E t is known. So, this can be written as 1 minus eta over eta prime over 1 plus eta over eta prime times twice E naught. So, these two equations allow me to solve the whole problem, because it gives me E r is equal to 1 minus eta over eta prime 1 plus eta over eta prime E naught. Now, what are these equations saying? Well, first of all, let us try some special cases. Supposing I have the same medium on both sides, supposing the glass is really air, then clearly mu over epsilon is the same on both sides. So, eta is equal to eta prime. So, 1 minus eta over eta prime is 0, there is no reflection, 1 plus 1 2, there is total transmission. So, if the same medium is on both sides, there is no reflection, all the energy is transmitted. Supposing on the other hand, you have eta or eta prime going to 0, then there is only reflection and there is no transmission. I hope I got that right. I will have to verify that. If I have to check the sign of that. So, you can try various different special cases. We will do that next time. That is, we will try the case of a superconductor, we will try the case of a very good conductor, and we will try the case of a normal dielectric. But it is all there in these equations. These two equations tell us how much is transmitted, how much is reflected. I will stop here for now.